Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into Section 1.3 from your textbook, which investigates a little bit more about existence and uniqueness theorems, as well as gives us a way of visualizing solutions to first-order differential equations. Before we get into that visualization, known as slope fields, we're going to talk a little bit about some existence and uniqueness theorems, because even though this is the very start of our class, we actually get two of the biggest sort of existence and uniqueness theorems for differential equations right away. So, recall from the sort of last video that we introduced and discussed an existence and uniqueness theorem that holds for linear differential equations. So, this is this theorem here. It says that if you have an nth order linear differential equation of the form where you've put it into the standard linear differential form, so that's the nth derivative of y plus a function of x times the n minus first derivative of y plus all the way down to a function of x times the first derivative of y plus a function of x times y, equals some function of x, and the only condition here, besides that this has to be a linear differential equation, is that all the functions are continuous on some interval I. Then any IVP where you have y of x0 equals y0, y prime at x0 equals y1, so on and so forth, where that x0 is in that interval where all the functions are continuous, is guaranteed to have a unique solution. A couple little notes here, just to make the notation sort of align with your textbook. When we initially stated this, we said these were like z's so that there wasn't confusion about x and y being repeated. But your textbook uses y here, so I just decided to use it on this statement of the theorem. Obviously, the letter or variable doesn't make any difference, but just to stay consistent with what your textbook is doing. So this is a very powerful existence and uniqueness theorem that we talked about in the previous video. This existence and uniqueness theorem applies to any order, right? It's nth order, but it must be a linear differential equation. And as I mentioned, as we investigate especially higher order differential equations near the end of our class, we pretty much focus exclusively on linear equations, linear differential equations, because there's such a sort of rich, extensive theory about their solutions. However, this does have the limitation of only applying to linear differential equations. Luckily, though, there is another powerful existence and uniqueness theorem that applies to any differential equation, provided it's first order. So we're going to talk about what is called the existence and uniqueness theorem for first order differential equations. So you got to keep in mind that after we have this discussion, you guys have two different existence and uniqueness theorems. One that applies to any order linear differential equation, and one that applies to only first order differential equations, both linear and nonlinear. So let's go ahead and look at this second existence and uniqueness theorem. So this is what's called the existence and uniqueness theorem for first order differential equations. So we're going to suppose that you have an initial value problem for a first order differential equation of this form. So a first order differential equation, again, could be linear, could be nonlinear, just as long as it's first order, can be written into this format, where you isolate the derivative of y on one side, and then you have some function of both x and y on the other. Keep in mind that since it's potentially nonlinear, there really can be a function of y on that right-hand side. Now, not every first-order differential equation initially comes in this format, but to apply this theorem, you have to put it into this format. And it is possible that, not possible, it is always doable that every first-order differential equation can be put into this format, but you might need to do a little bit of manipulation. And of course, since it's first order, right, the IVP just looks like y at x0 equals y0. Since it's only first order, you only have one initial condition for the IVP. So, what does this existence and uniqueness theorem say? Well, it says that if you have this IVP for this first-order differential equation, then if this function here and its partial derivative with respect to y. Notice this is the partial derivative with respect to y, because we're thinking about this as a function of both x and y here. If both the function and its partial with respect to y are both continuous, remember being continuous in multivariable situations is not continuous on an interval, it's actually continuous on a rectangle around the point x0, y0, which is the initial condition, then the IVP is guaranteed to have a unique solution. Once again, this statement here is both an existence statement. It says that the IVP will have a solution, and a uniqueness statement because it's saying that that solution will be unique. So, in other words, this theorem is basically, once again, about IVPs. In general, all existence and uniqueness theorems for differential equations apply to IVPs. They don't apply to solutions to the differential equation just by themselves, but they apply to solutions that have to satisfy a set of initial conditions. So this is saying that as long as this function and its partial with respect to y are both continuous near the initial condition, then it's guaranteed that the IVP will have a unique solution. A quick note here, especially because just at the beginning of our course, we're just starting to get into these more theoretical statements and everything. You should be aware that this is what we consider a one-directional theorem. What that means is that if these two things are true, if this function and its partial are both continuous, then you automatically know the IVP will have a unique solution. If for some reason this function or this partial are not continuous near x0, y0, then we cannot draw any conclusions. So that means that if one of the conditions above is not satisfied, we cannot draw any conclusions. In other words, if that function or its partial are actually discontinuous at that initial condition, then the IVP might have a unique solution, it might have many solutions, or might have no solutions at all. In other words, when these conditions fail, this existence and uniqueness theorem tells us nothing, and we'd have to just analyze it manually. Of course, we don't know how to analyze these things manually yet because we haven't learned how to solve anything, but it's just really important here to recognize the existence and uniqueness theorem is one-directional. It's saying if these two things happen, if the function and its partial are both continuous, then we have unique solutions. If those aren't true, then we have no information. So, with these two existence and uniqueness theorems, I'm just going to put them here together, we actually have a lot of information about existence and uniqueness for solutions to IVPs. We basically know that there are always unique solutions for IVPs for linear differential equations of any order, provided that the little component coefficient functions are all continuous. And we have a theorem that applies to all differential equations, linear or nonlinear, as long as they are first order. Of course, higher order nonlinear differential equations become much more complicated, and at least for our class, we're not going to state anything about existence and uniqueness for them. For right now, in pretty much the remainder of Chapter 1, we're going to be focusing on first order differential equations, so you're going to see a lot of reference to this theorem. Unfortunately, once again, even though these are so central theorems, the proof of these statements are a little bit beyond the scope of our class. If you look in your textbook, there's a reference to another textbook that actually does give a proof of this. You can tell that the proof must be pretty gnarly because the reference to the other textbook is a textbook back from like the 50s and 60s, and those sort of mathematical texts are always notorious for having some pretty difficult proofs. This particular proof is not undoable, but it is very beyond the scope of our class. So we're just going to state both these existence and uniqueness theorems without proof. Pretty much from here on out, though, most of the major theorems we're going to see in this class we will prove, but these two, unfortunately, they're just a little bit beyond the scope of our class. All right, so why do we want to know about this existence and uniqueness theorem? Well, it obviously is an essential part in terms of just the theory of differential equations, which as we're working through a mathematical subject, we always want to develop as much of a general theory as possible. But it turns out that this theorem also can help us a lot when trying to visualize. So we're going to talk a little bit about slope fields, talk about how this existence and uniqueness theorem applies to slope fields, and then take a look at an example. So, slope fields. So what is a slope field? Well, a slope field is simply a graph, and it's a graph that shows the slope of the solution curves to a differential equation at each point. So in other words, at each coordinate point, at each ordered pair on your standard coordinate axes, what you'll be graphing is the slope of the solution curve to whatever differential equation you're trying to analyze. Now that might sound like a lot of work trying to draw all these slopes, but it turns out that they're very useful and very sort of easy to construct because a first order differential equation is literally a formula that allows you to calculate the derivative based on x and y. When we write out a first order differential equation, if we put it into this sort of format, it's telling us the derivative based on x and y. So if we pick a particular xy coordinate, then if we plug into whatever the function is over here, that'll tell us the derivative at that point. So it's not too bad to use a first order differential equation and just plug in values to get the slope of the solution curve at each value. Then the sort of trick or the idea from that is if we trace the pattern present in those slopes, then we can actually sketch out the solution curves, meaning the graphs of the solutions to the differential equation, without ever needing to solve the differential equation. Now, this is a it's a really important idea here, because basically this is saying is that we can visualize the solutions to differential equations without needing to solve the differential equations. Now, of course, after we finish up section 1.3 and we start to move into 1.4 and beyond, we will start to learn how to solve differential equations. But the idea here is that for really complicated differential equations, you could theoretically avoid solving them and just use a graphical approach, especially if you had access to software or a computer or something like that, and be able to visualize the solutions without ever needing to solve it. If you guys ever take more advanced differential equations, specifically in partial differential equations, in other words, like multivariate differential equations, visual approaches and understanding visualizations of solutions is one of the major ways that people work in that field, because actually solving things turns out to be tremendously difficult. So for us, we're talking about this as sort of an introduction, and then we'll learn how to solve things so we can sort of confirm our results. But just keep in mind that as things get more complex, especially in other courses or in like applied fields, being able to visualize is a tremendous asset, especially if you don't actually need to solve anything. So this is what a slope field is. In just a moment, we'll actually go ahead and take a look at building a slope field. But let's first talk a little bit about how slope fields in the existence and uniqueness theorem sort of play together. So the existence and uniqueness theorem for first-order differential equations is a powerful tool when combined with slope fields. If you can show that every IVP has a unique solution for whatever differential equation you're looking at, then that means that when you look at those solution curves on your slope field, they can never intersect. Because if you had two solution curves that intersected, they would both solve the IVP at that point of intersection. So if you can use the existence and uniqueness theorem to show that there are always unique solutions, that means every solution curve is separate and does not intersect each other. That can make things much easier when drawing in a slope field. The last sort of important concept that we're going to make use of is just a very short definition, and it's just a nice use, especially when combined with these two topics here. This we'll see in a moment. So just be aware that if you guys ever see mention of an equilibrium solution to a differential equation is a solution of the form y equals a constant. So solutions in general are functions, and we're saying that a very special type of solution, again, not every differential equation is going to have equilibrium solutions, but if you can find solutions that are just constants, y equals a value, in other words, visually just horizontal lines, we call those equilibrium solutions. All right, let's put all this together and take a look at an example here. So we're going to consider this differential equation. We've got y prime equals y squared minus 4. Notice that this is a first order. We'll just make a little note here. This is first order. But this guy is nonlinear. Why is it nonlinear? Because we have a function applied to our dependent variable. We have that y squared there. So we're going to do a couple things with this. First, we're going to prove that every IVP associated with this differential equation will have a unique solution. So in other words, we're going to show that any IVP we come up with for this thing is guaranteed to have a unique solution. Then we're going to determine all the equilibrium solutions for this differential equation, and then we're going to try to sketch a slope field. And this is a very standard sort of trio of things to do together, because you want to sort of start by knowing that the IVPs will have unique solutions, then you want to figure out any of these equilibrium solutions, and then put all that together, and they'll help you draw the sort of slope field. So you can sort of think about steps A and B as being preliminary things to drawing that slope field. So let's start with A. So for A, we want to try to use the existence and uniqueness theorem for first order differential equations. So let's think about this as an IVP here. All right, so let's think about this as an IVP. So we'll think about it as y prime equals y squared minus 4. And we'll think about it as y of x0 equals y0. So we don't know what x0 and y0 is because we're saying every IVP. So in terms of the language of the existence and uniqueness theorem for first order differential equations, we would say that the f of xy here is actually equal to y squared minus 4, right? Because we have it y prime equals a function of x and y. Now, of course, there aren't any x's over here, but there we've got it into that format there. Now, if we then think about the partial with respect to y, the partial with respect to y of this is going to be 2y. So we have f of xy is y squared minus 4, and the partial of f with respect to y is 2y. What do we know about both of these? Well, these are both definitely continuous everywhere. So these are continuous everywhere. So since the function over here and its partial with respect to y are continuous everywhere, that means by the existence and uniqueness theorem for first order differential equations that every IVP is going to have a unique solution. So by u plus u theorem for first order equations, every IVP will have unique solution. That's guaranteed. That's what we just get from there. Nice and easy. As long as you have it in that format of y prime equals a function of x and y, then as long as you can check that that function, whatever is over here, and its partial with respect to y are continuous everywhere, then you immediately know that every IVP will have a unique solution. All right, let's think about equilibrium solutions. So remember, an equilibrium solution is y equals k. So we're going to think about things where y is a constant. Obviously, if y is a constant, its derivative is 0. So if we plug in, we're solving 0 equals k squared minus 4. So we're taking our differential equation. We're going to assume that the solution has this format. If y is equal to a constant, its derivative is going to be 0. Then we're just plugging in k for y then. Can we solve this? Is it going to have any solutions? Well, we would have 0. We'd have 4 equals k squared, and we'd have k equals plus or minus 2. So we'd say that there are two equilibrium solutions, y equals 2 and y equals negative 2. So there are two constant functions, two horizontal lines that are solution curves to our differential equation. All right, now let's go ahead and actually look at building our slope field. So we'll give ourselves another page here, zoom in a little bit, and we'll go to part C here. So for part C, we want to actually try to build our slope field. And what information do we have so far? From A, we know all, well, we can say solution curves never intersect. So the solution curves can never run into each other because every IVP has a unique solution. And from B, we know that we have equilibrium solutions at y equals negative 2, y equals 2. And remember, our actual differential equation is y prime equals y squared minus 4. All right, so let's draw ourselves a coordinate axes here. We'll label some values, 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3. Okay, so let's first talk about how we can put these equilibrium solutions on here. What this basically is telling us is that whenever y is negative 2 or 2, we know that the derivative is going to be 0. What does it mean to be a derivative of 0? Well, visually, we would draw a derivative of 0 to be a horizontal line. So at something like y equals 2, anytime y is equal to 2, we have horizontal slopes there. And notice I'm just putting them at the integer values. Technically, they're also in between at every point where y is equal to 2. You always have a horizontal line. Now notice that if we were to fill that in, like if you start at one of those and you follow the slope, since it's horizontal, you would just move across like that, and that's giving us that equilibrium solution there. Right? We said that an equilibrium solution is going to be a horizontal line, so if you start on there, you would just follow that slope and always remain there. All right, same thing down here. Whenever y is negative 2, right, we would have a slope of 0, which is a horizontal slope there. Okay. All right. What about at other values? Well, we can make a little table. Notice that we only need to input y values because x doesn't show up at all. So this is an easier case. We'll see more advanced ones in our next video. So we have y prime equals y squared minus 4. So let's think about some other y values. What happens when, say, y is like 1 or minus 1, or maybe like when y is 0, or maybe like when y is like 3 or minus 3? Well, when y is 1, then y prime, right, we get y prime is going to be negative 3. So let's think about what that tells us. That tells us whenever y is equal to 1, regardless of what x is, the derivative is negative 3. So what does it mean to have a derivative of negative 3? Well, a derivative of negative 3 would be a pretty steep negative slope. So whenever like y is 1, so anywhere along here, we should draw in slopes that look like negative 3. Now, you just got to sort of do that as best as you can. So let's just sort of draw in some pretty steep negative slopes. And each of those, I'm trying my best to make them look the same, because each of those are supposed to be a -3 slope. All right, what about when y is -1? Well, if you plug in -1, you get y prime is also -3. So whenever y is -1 along here, we should have similar sort of looking slopes. So again, pretty steep negative slopes anytime y is -1. Now again, remember, this is an easier case because there's no x value, so as soon as we know what happens at a y value, we can just fill in the entire horizontal row of slopes there. What about at y equals 0? Well, that would give us y prime is -4. So that would be along here, we'd have even a steeper negative slope. Right? So we will make it even a little bit steeper. All right, there we go. What about at things like 3 and -3? Well, at 3, we'd have y prime equals 5. So that would be a steep positive slope. So we'd have something that maybe looks like that. And then at -3, we'd have y prime also equals to 5. So we'd have sort of a steep positive slope here. Okay. So now let's see, so we filled all this stuff in, again, just by plugging in values. Notice this is what we meant by that the slope fields are, they're a little messy, but they're relatively easy to generate. You're just plugging in values, and then the differential equation, since it's an equation about the derivative, literally tells us the slope to draw. Now we want to try to draw in what the solution curves look like. So let's start by drawing in the ones that fit that equilibrium, right? If you start along here, right, we'd have just a solution curve that goes like that. And of course, we'd also have something that would go along here. Now, the reason I want to call attention to those is, remember, we have this other piece of information. The solution curves never intersect. So what goes on in here can't cross these lines, because then we'd have an intersection. So let's think about what happens in there. Well, imagine you started here. Well, what would happen is that you would have a very sort of steep negative slope. But then when you hit here, remember this is a slope of -4, you'd have a less steep negative slope, -3. And as you approach closer and closer down here, you would have to actually make sure that your slope gets less and less negative. Imagine plugging in something like say -1.9 into here, you'd have a very slight negative slope. So in other words, what's going to happen is that this thing is going to sort of come down and then approach like that. But it can't intersect, so it must be sort of asymptotic there. What about over here? Well, it's got to be the same thing. It's got to sort of match these slopes here. So again, still got to have sort of a slight negative slope and then become asymptotic there. Now, what if I drew in starting from here? Well, what would happen is that it would fit perfectly in. What would happen up here is it would sort of scoot in there, and then down here it would scoot in right above. If we did one here, then it would sort of scoot in there and then scoot in like that. And they would layer on top of each other, but they would never intersect. What about up here? Well, it should be pretty clear. It's got to follow this positive slope. More and more it goes up, it's going to get steeper and steeper. And then, of course, here, it's going to have to come in and fit that equilibrium solution. So notice these equilibrium solutions often act like asymptotes there. And then finally, here, we'd have to have where it has sort of a steep positive, and then it would approach in like that, and then look something like it would just continue down like that. So there we go. These are what the solution curves look like, what typical solution curves look like. And in each section, if we change the initial condition, notice I was using sort of initial conditions where like x was 0, but it doesn't matter. If we chose here, you'd have something that looks similar, but it would sort of just be tucked in over, right? It would be a little bit off to the side. Here, if we did something like this, it would sort of scoot in like there, never intersecting, and like that. So each of these represent the unique solution to the IVP. So this guy right here would be the unique solution to the IVP with 0, 0 as the initial condition because it went through that point 0, 0. This guy would be like the unique solution for, I guess that would be like 0, -3. This guy would be the one for 0, 3, so on and so forth. If we picked an initial condition where you had y equals 2, so say like 0, 2, then you'd be following this your unique solution would be the equilibrium solution. So we can actually sort of know what happens in our differential equation without ever solving it. This is going to become an even more important analysis as we go further on and we learn to do some modeling with differential equations, because these things tell us about the sort of end behaviors. If you think about this as like sort of limits, imagine you start here. Well, according to this, as you sort of follow on, you're going to tend down to this -2 there, right? If we were sort of imagining you're moving this way. If you start here, you'll also tend that way. But if you start up here, you actually would blow up towards positive infinity. So your starting condition would tell you where you would sort of end or where you would head overall in the long run. That's why these are often referenced as equilibrium solutions, because sometimes the solution curves tend to those in the long run. Okay, so this is just our first example of building a slope field. And this is about as sort of simple as a slope field can be, because we had this advantage that everything on that right-hand side was in terms of y. So we only had to plug in y values, and then whatever slope we got applied for any x value, as long as we were on that single y value. In our next video, we won't introduce any new concepts, but we'll do a couple more examples of building slope fields for slightly more complicated differential equations, specifically ones that involve both x and y on the right-hand side, and we'll learn some tricks for trying to draw those a little bit more efficiently.